we are going to work through this problem on how to calculate the Ka value for a weak acid. This is the same practice problem that's in your PowerPoint notes, so feel free to print this particular sheet out. I'll put it in Google Classroom, and you can work through this practice problem on this sheet. So it says a student prepared a 0.1 molar solution of formic acid and found its pH at 25 degrees Celsius to be 2.38. Calculate the Ka for formic acid at this temperature. Now, recognize formic acid is not one of the strong acids that we know. So the very first thing we're going to do is we're going to go ahead and we're going to write out the equation for the equilibrium reaction. Since this is a weak acid, it's going to be in equilibrium. So HCOOH is going to be in equilibrium with the proton that it donates and the ion that is left over. Now we're going to go ahead and we're going to write the equilibrium expression. Since this is Ka, it's going to be just like the other equilibrium expressions that we've written. Since everything here is aqueous, I'm going to go ahead and add that in there. We're not dealing with a solid that disassociates just a little bit. We're dealing with something that is aqueous. It's going to, again, be products over reactants. So our Ka value is going to be the concentration of H plus times the concentration of formate, which is HCOO minus, all over the concentration of our acid, which is formic acid, HCOOH. Okay, so let me get rid of some of these marks. Let's go down. We'll scroll down here a little bit. Now what we're going to do is we're going to calculate the concentration of H from the measured pH. Now, if you take a look at your equation sheet, you guys will see you have pH equals negative log of the concentration of H plus. And we know that the pH is 2.38. So what we really need to do is we need to rearrange this so we can calculate the concentration of H plus. So I'll do this kind of stepwise. The log of the concentration of H plus is equal to negative 2.38. And so in order to get the concentration of H plus, we're going to take that 10 to the x. And so we're going to get 10 to the negative 2.38. And if you calculate that out, you're going to get a concentration of 4.2 times 10 to the negative third molar. I want to comment on something really quick. If the pH has 2 decimal places, like this one does, 2.38, that is the number of significant figures in my concentration. You can Google that if you want to and see why they do it that way, or ask me later and we can talk about it. Okay, so now that we know the concentration of H, we can make an ice table. So remember, our job was to calculate Ka. And so in order to calculate Ka, we need to know the concentrations of all of our species. Now we know the concentration of H plus, which is also going to be the concentration of our formate ion. Let's go ahead and we'll set this ice table up. And again, I'm just going to do it this way. We've got our formic acid, HCOOH, and then we have H plus, and we have formate, HCOO minus, and ICE. So initially, our concentration was 0.1 molar. We didn't have any H plus or any of the formate ion. The change is going to be minus x. Here it's going to be plus x, and here it's going to be plus x. Now, according to our calculation, we know that x is equal to 4.2 times 10 to the negative third. So this is going to become 4.2 times 10 to the negative third. 4.2 times 10 to the negative third. And then our acid is going to be 0.10 minus x, which is minus 4.2 times 10 to the negative third. Now, if we take a look at that, that actually is not going to change that number at all. So since the small amount of formate ionizes compared to the initial concentration, the number of significant figures that we're using, the subtraction yields the same concentration. Therefore, we're going to use 0.1 molar as the concentration. This approximation is acceptable if the percent ionization is less than 5%, or if Ka is less than 1 times 10 to the negative fourth. We've talked about that before, about being able to make that approximation, and we can use that same philosophy here as we did before with Kc's. Makes things easy so we don't have to use the quadratic equation. So we're going to go ahead and we're going to plug that in for Ka. So Ka is going to be equal to 4.2 times 10 to the negative third. And I'm just going to go ahead and square that because it's concentration of, I'm going to scroll back up here. Right here, if we take a look at that, both of those concentrations are the same. So just oops, shortens my writing a little bit. Let's see if I can scroll back up there. That's a second problem. And then I'm going to put that all over 0.10. And so we end up getting a Ka value of 1.8 times 10 to the negative fourth. Okay. No units on this at all. And then I added one more question in here because you might have a few of these in your problems. In your problem set, calculate the percent of acetic acid that is ionized. Percent ionization, just a reminder, is going to be the concentration of H plus over the concentration of the acid. And I'm going to go ahead and use HA as my acid. And this is going to be at equilibrium, and this is going to be initial. So in other words, we're just comparing how much H plus or proton the weak acid had given up. And then to get a percent, we're going to multiply that by 100. So it's going to be 4.2 times 10 to the negative third all over 0.10. And then times 100 gives us a percent of 4.2%. And again, we can see that this percent ionization is less than 5%. So we know that our approximation is acceptable because of that. Hopefully this looks familiar to you guys. I am actually going to scroll down here, and I have a second problem where it's hydrofluoric acid. Again, it's a weak solution, or a weak acid in solution, and this time they give you the Ka value and they're asking you to find the pH. So I'm going to work through this one, kind of watch how this one goes. You'll see a lot of the similar beginning steps. We're just going to kind of rearrange things because now we're starting with Ka. So again, I'm going to start by writing the equilibrium expression, or the reaction. Sorry, my bad. So it's hydrofluoric acid. Again, this is aqueous. I'm going to write the physical states because that reminds me that this is not a KSP. It's going to break up into, or dissociate into, some H plus ions and some F minus ions. Now, the Ka value is really, really small. And so the equilibrium expression ends up being 7.2 times 10 to the negative fourth. And that's going to be equal to products over reactants again. So H plus times the concentration of F minus all over the concentration of HF, hydrofluoric acid. Okay, now I'm going to make an ice table. I'm actually going to make my ice table right here. So ICE, cheat a little bit right here. Sort of wall that off a little bit. So my initial concentration of hydrofluoric acid is 1.0, and I don't have any dissociation yet. My change is minus X plus X plus X. Everything is a 1-to-1-to-1 ratio. So at equilibrium, I would experience 1.0 minus X, X, and X. Now, again, going back and taking a look at that Ka value, you probably would think we could ignore it. And we can. It's 7.2 times 10 to the negative fourth. So we should be able to ignore this when we stick it into our expression and solve for x. So we end up with, I'm actually going to just draw a little arrow here so I can kind of keep this on the same screen a little bit. No, not that small. There we go. So if we plug this in, we get 7.2 times 10 to the negative fourth equals x times x, or x squared, all over 1.0. And so I end up with x squared equals 7.2 times 10 to the negative fourth. And I'm going to take the square root of both, and I end up with x equals 0.027. All right, so that's our x value. So here's what we're going to do. So we solved for x, and if we go down, it says write the equilibrium concentration for each. So basically, the concentration of HF is still going to be the same, 1.0 molar, but my concentration of H plus ion and my concentration of F minus ion is going to be equal to X, which is 0.027 molar. All right, so to calculate the pH from the concentration of H, now I have that number, I can just plug it in. pH is equal to the negative log of the concentration of H plus, which is the negative log of 0.027, and that gives me a pH of 1.57. And again, two significant digits on that concentration, so I'm going to go 2 places past the decimal on my pH. Now that should make sense because hydrofluoric is an acid, and that is a pretty low pH, which is signaling that I have an acid. Hopefully that gives you enough to get through the practice problems. I'm still gonna, read through the PowerPoint notes. Please let me know if you have any questions.